I'm Ivey O'Neill.
And I'm Delaney.
And we're doing projectile motion.
Of this baby.
So what we're doing is we're measuring the projectile motion of this baby from the front of the car. So we're going to accelerate to about 4.5 meters per second, and then we're going to come to an abrupt stop and measure the baby's projectile motion from the front of the car to the ground.
Ready?
Okay, I'm going to accelerate to 4.5 meters per second and then abruptly stop. Did it work?
I think so. Okay, so I just got out of my car. I haven't moved it at all. This is where I stopped it, and that's where the baby's landed. And Delaney's going to measure from the top of the baby's head to the base of the car. I'll help you.
Hold that.
Okay.
Alright, wait, does that look like the base?
Yeah.
Yeah. Hold on, actually, I'm just going to pull it out a little bit more so that we're a little more accurate. Keep holding it. Okay. So it's 500 millimeters, 50. It's about 58 centimeters. So the baby landed a meter and about 58 centimeters from the base of the car. This is trial 2. Alright, in trial 2, it went 98 centimeters. Oh, trial 3.
Alright, we're videoing for trial 3 from the head to the base of the car.
Will you stretch that?
Yeah.
Yeah, that's right. Alright, this one was 1 meter and 43 centimeters, so closer to trial 1 than trial 2 was. Okay, so we're converting 10 miles per hour to meters per second. So what we're going to do is we're going to start with the fact that there is 10 miles per 3,600 seconds, which equals about 0.0028. So then we have 0.621 miles in 1 kilometer, and we're going to put our 0.028 miles per x kilometers. So we're just using a proportion to find how many kilometers per second it is. So we have, there's about 0.0045 kilometers per second, and then we have to change that to meters per second. So there's 1,000 kilometers in 1 meter. So it's 4.5 meters per second. So when the car is traveling at 10 miles per hour, it's traveling at 4.5 meters per second.
Now we are going to find how long it should take the baby to hit the ground, finding the horizontal distance. These are our variables. This is the initial height of the baby on the license plate. And we're trying to find t. So I plug it into my formula. 0 equals 1/2 -10, which is g, t squared plus 0.84. Negative 0.84 meters. No.
That's right.
Then we find t is the square root of 0.168, which is 0.41 seconds is the time.
So now we're going to find the horizontal distance predicted by the time that we found. So we're going to take our time, which is 0.41 seconds, and we're going to put it into the equation. Change of x equals v of x times t. So our change of x is going to equal 4.5 meters per second times 0.41 seconds. So the change in x equals 1.845 meters. That's what it should equal.
That's what should equal.
The horizontal distance
Okay.
should be 1.845 meters.
So the horizontal distance for trial 1 was 1.58 meters. For trial 2, it was 0.98 meters. And for trial 3, it was 1.43 meters. Now to find the time it took, we do 1.58 equals 4.5 t, and we find the time for that one was 0.351 seconds. For this one, the time was 0.218 seconds, and for trial 3, it was 0.318 seconds. Oh, and we use the equation change of x equals 4.5 meters per second times time.
So now we're just going to compare our predicted values with the actual values. Our predicted time for the baby's descent was 0.41 seconds, and the predicted horizontal range was 1.845 meters. So you can see that in each of our actual trials, the predicted horizontal distance and the predicted time were less. Or in each of our trials, the horizontal range and the time were less than the predicted horizontal range and time. And we think the reason for that was because in our actual situation, we couldn't keep the braking time as a control. So considering the fact that we couldn't go from 10 miles per hour to 0 miles per hour in exactly 1 second, we had to take into account that the baby was probably traveling at a little under 4.5 meters per second because of the braking time. So if there wasn't any braking time taken into account, that would be the horizontal range and the time. And with that taken into account, you can see the horizontal range and time varies.
This is our data, our independent and dependent variables, and then our trial 1 and trial 2 and trial 3 data. This is our graph. It's a motion map, and instead of each vector being a second, Each vector is a tenth of a second.
So you have the baby starts right there, and that's its horizontal velocity, which doesn't change, and its velocity in y is accelerating or increasing.